So this presentation is the poster of the paper that has been presented yesterday in the first session. So if you did not attend yesterday, you can see this shorter version.
Additive manufacturing with solid wood. Additive manufacturing, 3D printing, rapid prototyping. When we hear these terms, we all have a very specific image in mind. Futuristic, cool, and accurate. The idea of realizing designs that just came across our minds in no time is pretty amazing. However, what is probably the future of manufacturing houses one major problem that we fastly forget about: sustainability. Yes, many of you may scream at me now with the intention to say that PLA is a sustainable and environmentally friendly material. And you are kind of correct. While PLA is a thermoplastic made of cornstarch, it claims to be 100% biodegradable and therefore would be the material for sustainable additive manufacturing. However, as it is a thermoplastic, it still can take over several thousand years to completely decompose in an uncontrolled and natural environment. It is on us to find a new material that is suitable for additive manufacturing while meeting the goals of being sustainable. Of course, there are several other types of additive manufacturing that uses different materials such as resins or metal. While the process of printing is different, for example melting metal powder or hardening UV-activated resin, none of these mentioned materials can meet the aimed target of sustainability, but instead are being harmful to the environment, not being renewable or recyclable. As a new technique, we have developed an additive manufacturing method using a wooden filament made of a fast-growing local plant, wicker twigs. This technique enables direct and laminated wood filament extrusion without the use of thermoplastics. A good source for this fast-growing material are twigs of a willow shrub. This material is currently researched by over 2 years at the University of Kassel in several co-working departments. The material has several properties that compensate the concerned problems. Renewable and biodegradable. A willow shrub can be harvested over several months, as one shrub can grow up to 2.5 meters in a year. These are the raw material twigs you can buy, split at the profile center point. With milling bits, the top and bottom part of the twigs get cut to make sure to get rid of the surface curvature. The second step cuts down the sides of the twigs to get a constant filament string profile. The most material efficient width and height for a constant profile turned out to be 3 by 0.6 millimeters. This new material shares one comparable important characteristics to filaments used in FDM printers. It allows possible surface curvatures of printed objects up to a breaking point of 20 millimeters. In addition, the tensile strength of one wicker twig is greater than any pure thermoplastics. As a wicker string will only bend with its flat surface direction, multiple filament strings are combined to join and create one composite and square extrusion. This technique has the advantage of being able to stack the extrusion in layers. The extrusion can keep its applied curvature due to the combined filament's differential length in occurring curvatures. For combining the willow filament strings and a fast additive manufacturing process, an adhesive system had to be chosen. Our method requires a fast drying and binding time at an affordable price. As the material itself can be manufactured inexpensively, suitable adhesives should be equivalently economic. Several adhesives, such as white glues, UV resins, and contact adhesives, were tested. With several contact adhesives, we laminated the filament strings and left them dry for 24 hours. The laminated and dry strings are then reactivated by applying heat of a temperature of around 50 degrees Celsius. By pressing the single filament strips together, a combined square extrusion can be produced. This adhesive is currently fitting our manufacturing and parameter constraints. Other gluten-based glues share the same characteristics and could also be investigated due to its reusable and sustainable characteristics that fit the overall goal of this research. As a first extruder design, the previously mentioned techniques and principles must be considered. The 4 filament strips are guided through an aligning part, a cutting section, the heating block and the nozzle to be combined into one square extrusion. The filament strings are pushed and pulled by 3 NEMA 17 stepper motors. The heating block is controlled by a PID circuit using an Arduino Uno, as well as the stepper motors. The nozzle consists of one silicon roller, one geared roller and one funnel. Together, they press and guide the strings together to one compound heated string, while the funnel guides the filament to the print bed and applies slight pressure to it. The idea of combining the strings within the extruder addresses the individual string length within a printed surface curvature. By combining the laminated strings with heat, the printed and cooled down extrusion can keep its given curvature. The initial testing of the extruder provided promising results with only a small deviation. For a good first layer adhesion, the print bed was coated with a thin layer of the compound material. The printing angle, the angle between the extruding filament and the print bed, was set to 10 degrees to make good contact with the print bed while minimizing the distance between the nozzle and the print bed itself. A greater angle led to a twisting behavior of the extrusion that drastically reduces the accuracy while printing. 4 layers were printed on top of each other with an increasing offset to test the overhang capabilities. An overhang angle of 22.5 degrees was saved as a maximum parameter to print solid shells. Now we have seen the potential of printing with solid wood. To forestall and address arising questions about a possible use case, we first have to look at the performance between the layers. Samples of 15 cm in height, or 50 layers, and 4 cm in width were tested for their tensile strength against the fiber and layer direction. Without the reinforcement layer, the layer adhesion is only as strong as the adhesion strength of the used compound. With an additional reinforcement layer, the part can withstand a maximal standard tensile force of 1900 Newton. A slicer was developed in Grasshopper, which slices an input geometry into its individual layers. In addition, the slicer shows improper design choices that cannot be printed partially. The slicer checks every layer for its occurring curvature and overhang angle, so a designer can check his design before printing. As an output, closed curves or layers are produced. The tests provided valuable results, which were taken into a differential curve growth algorithm in which the curve develops itself within its given constraints and rules. The computational approach was developed to test a maximum possible self-developing design. A simple circle was defined as an input. In iterations, the curve splits itself into smaller parts or segments, which then are used in the kangaroo physics solver. These segments were given spring force characteristics to allow an overall growth of the input curve. Colliders in each endpoint of a segment prevent the curve of one iteration from crossing itself, to make sure that the radii of the curvature stay always within its printable maximum. In every iteration, the curve grows while traveling in the z direction within the layer height. An additional rotation parameter was applied to add a twisting behavior. This approach can take every curve as a basic input and creates growing designs through its maximum parameters as inputs. As a next step, we combined an ABB 1200 series with an additional rotating axis for continuous helical prints without the need of cutting the material to give the design a continuous strength within its shell. For extrusion, a faster speed could be easily set up by using bigger stepper motors. A first part of the column design was also printed. This research accumulates several benefits and visions of additive manufacturing with wood. Current methods of 3D printing with wood as compound material, for example, used in FDM or fused deposition modeling printers, can imitate up to a certain extent the visual appearance of wood and are open to the consumer market. However, this compound material only has a small proportion, up to 40% of groundwood. While the percentage of this wooden content may increase in the future, this only imitates the overall look and color scheme of wood and does not take over its mechanical characteristics, like its tensile strength and anisotropy, due to the lack of long fibers. In comparison, the treated wicker twigs create a combined filament with a greater tensile strength of real solid wicker. This makes wood the largest proportion of this extrusion. The technique, however, is more related to automatic tape layering, but in an upright printing orientation. Both methods require a pre-laminated tape, in this case a treated wicker twig that gets printed or layered. Due to the upright printing, this printing technique is in its results comparable to an FDM printing approach. The printing process shows various advantages in printing with combined wicker twigs. For example, the overall printing speed compared to a traditional used FDM and SEL 3-dimensional printing methods is improved by having a solid material and a larger filament profile. However, the main trade-off between this new and the traditional techniques is the limitation in printing in a smaller scale. Considering the filament scale, the maximum printable radius of curvature is very acceptable for architectural and furniture scales. The overall printing strength highly depends on the filament surface finish after its treatment and the glue lamination. This behavior occurs in traditional 3-dimensional printing as well. By adding infill or additional perimeter shells, greater overall strength can be reached. An additional orthogonal printing layer on the outer shell can be considered. With this layer combination, the design strength can be greatly improved, especially in its layer adhesion direction. The hypothesis about the possibility of printing an alternative and solid wooden filament in 3D space is supported within this ongoing research. With today's possibilities and the precise application of machinery, wooden elements can be produced that are consistent in their dimension to use them as a raw material for solid filament production. Combining these filament strings with a compound material creates a lamination bond between layers and therefore can be produced three-dimensional objects by layering. For a consumer market, a simple 4-axis system can be drastically decrease the production cost. With this prototype of wood printing, further research investigations are made.